Okay, so we've talked about some reactions of aromatic compounds, right? So if we take benzene and we treat this with Cl2 and FeCl3, we know that we can substitute one of the hydrogens with a chlorine, right? And because we started with a symmetric compound benzene, it doesn't matter where you put the chlorine, right? You can put the chlorine in any position because it's the exact same molecule, right? These three molecules are identical. They're the same molecules. They're just rotated by 60 degrees or 100 degrees. The question I want to pose in this video is, what if we have a substituent group already on our ring? So what if we start with ethylbenzene? So if we treat ethylbenzene with Cl2 and FeCl3, we know this reaction is going to substitute a chlorine, a hydrogen with a chlorine, but the question is where? Okay, so there are three isomers that we could form. We could add the chlorine to the ortho position. We could add the chlorine to the para position. Or we could add the chlorine to the meta position. So there's really three compounds, okay, that we can form. And the question is, what is the major product, or what are the major products? And again, here I've drawn the chlorine on the right side at the ortho. It could also be on the left, right? Here I've drawn the chlorine at the meta position on the right. It could also be on the left. If we only add one chlorine, it doesn't matter if it's on the right or the left. It's the same compound if you just flip it. So there's three possible compounds we can form. Again, just a reminder, this is the ortho position. Here I have the para position, and here I have the meta position in relation to the ethyl group that I started with, right? So it's important to remember ortho, meta, and para, all right? So the question is, what is our major product, all right? To do that, we really have to understand the group that is on our benzene ring to begin with. This group here is going to direct where the chlorination happens, okay? And we have a table to really show this. Okay, so we're going to look at the effect of substituent groups on our EAS reaction. And there's two columns here. The column on the left, the groups listed are ortho-para directors. So these groups on the left are going to direct the substitution to be at the ortho and or the para position. On the right, these groups are all meta directors. They will direct the reaction to happen at the meta position. Okay? So let's take a look at all of these groups and how they can either be ortho-para directors, right? So we have two options. You can be an ortho-para director, or you can be a meta director. Before we do that, I just want to kind of talk about a term. You're going to see some terms here. We've separated ortho-para directors into strongly activating, right? So our groups can be strongly activating, moderately activating, or weakly deactivating. We have one group here on the left that's actually deactivating. All the meta directors are deactivating, and we'll see what that means a little later on. Activating means that the group will react faster than benzene, so the intermediate will be more stable, right? The carbocation intermediate, when we have these groups, will be more stable than the intermediate we have for benzene. So when it's activating, the carbocation intermediate is more stable than the benzene carbocation intermediate. When your group is deactivating, that means that the carbocation intermediate is less stable. So the carbocation intermediate is less stable than the carbocation intermediate of benzene. Okay, so first let's just look at this column here, see how we can help remember these. Remember, AR stands for an aromatic ring. So we can look at our simplest example here, just a benzene ring. So if we have ARNH2, we can think of this as a benzene ring and NH2. So AR is an aromatic ring, and for this example, we can think of those all as benzene rings, okay? So anytime the atom that's attached to the benzene ring has a lone pair, it will be an ortho para director. N has a lone pair, O has two lone pairs, O has two lone pairs, O has two lone pairs, or N has two lone pairs, or N has one lone pair. So all of these groups, the atom that's directly attached to our benzene ring has a lone pair. Those are all ortho para directors, and you'll see that those are all activating. They react faster than benzene. So when you have an N with a lone pair or an O with a lone pair directly attached to our benzene ring, that is an ortho para director, and it is activating. Okay? That's our first category, anything with a lone pair. Any alkyl group is also an ortho para director. Okay? So if you have a methyl or an ethyl or an isopropyl, any carbons, those are also ortho para directors. They don't react as fast, they're weakly activating, but they're still ortho para directors. And then our last category for ortho para directors are halogens. So anytime you have a halogen, right, remember halogens have lone pairs, these are going to be ortho para directors, but they happen to be deactivating. Okay, so we have three classes of ortho para directors. Anything with a lone pair, any N or O with a lone pair are ortho para directors. Any alkyl group, methyl, ethyl, propyl, butyl, those are all ortho para directors. And then any halogen is an ortho para director. On the right side, here we have our meta-directors. Meta-directors, okay? All of our meta-directors, they are all deactivating. They react slower than benzene, okay? So our first example here, we have a nitro group, okay, ARNO2, so that's a benzene ring directly attached to an NO2 group. And I want to remind you, when you draw this out, that nitrogen does not have a lone pair, right? That nitrogen does not have a lone pair. In fact, that nitrogen has a positive charge. Okay, so that nitrogen is different. This one does not have a lone pair, therefore it's a meta-director. So here we have a nitrile, a CN, SO3H. Any carbonyl groups are all meta-directors. So in this example, we have benzene rings, and the atom that's directly attached to it, this atom, either an N or a C, this position here is going to have some sort of double bond. It will be sp2 or sp hybridized. Okay, so we have an N double bond to an O, C triple bond to an N, SO3 has two double bonds, and any ketone, aldehyde, carboxylic acid, or ester. These all have our sp2 carbons. Those are all meta-directors. Okay, those are meta-directors. So step one here is really kind of memorizing or learning this table. Okay, that's the first thing we need to do, is really learn this table. So let's look at a couple examples here. Okay, and I want to highlight this. Our starting material here is toluene. So here we know we have a methyl group, right? Our methyl group. And that's important because this is going to tell you where you add your group. Okay? The reagents are always going to tell you what you add. So when we have Br2 and FeCl3, we know we're going to add a bromine. Where do we add the bromine? The methyl will tell us. So if we go back and look at our table, a methyl, right, is an ortho para director. So that means in this reaction, we're going to be adding a bromine to the para position and to the ortho position. Okay, we're generally going to be forming two compounds here. We're going to be forming para-bromo-toluene or ortho-bromo-toluene. Okay, and in my class, just to make things a little bit simpler, right, when I ask this, usually para is the major product formed. So usually you form a little more of the para product versus the ortho. So to keep things simple in my class, if I ask you to draw the product, you can just draw the para product if it's ortho and para, okay? So again, you will form a good amount of the para and the ortho. Those two together will be the major product, but generally I'll ask you to just draw the para product in my instructions. Okay, let's look at another example here. So now I start with benzene, right? Our first reaction, HNO3, H2SO4, that will add a nitro group. We can add this to any one of our carbons. So we substitute a hydrogen for a nitro group. That can go anywhere. So this is the product we get after step 1. Now, what do we need to know for our second reaction? Right, our second reaction, we need to remember that NO2 is a meta-director. So the ethyl group, right here we're doing a Friedel-Crafts 8 alkylation. We're doing a Friedel-Crafts alkylation, adding an ethyl group. That ethyl will be added to the meta position. So this is the meta position compared to the NO2 because the NO2 is already on it. The NO2 has been added first. Step 1, we add our NO2. Our nitro group is a meta-director, ortho, meta, para. So that means we add our ethyl group, ETBR, our Friedel-Crafts alkylation adds our ethyl. That ethyl will be added to the meta position. All right, let's look at another example here. Again, we start with benzene. Our first reaction, we're adding bromopropane, AlCl3. So this is a Friedel-Crafts alkylation reaction. Because we're starting with benzene, we can add that anywhere. So we do our Friedel-Crafts alkylation, right? We add our 3 carbons. We should note that there was a rearrangement here, right? That can occur with Friedel-Crafts alkylation, right? So we add our isopropyl group now to our benzene ring. So this is the product we get after step 1. Okay, that's the product after step 1. Right, the isopropyl group is formed because of a rearrangement, right? Now, what type of director is an isopropyl group? This is an alkyl group. Alkyl groups are ortho-para directors. Okay, so we're going to now add the NO2 group to the ortho and para position. Okay, so here the isopropyl was added first. Second, we add our nitro group. That's added to the para position, right? And again, we are definitely forming some of the ortho compound. So we're absolutely forming a substantial amount of the ortho isomer. But in my class, when I ask this, you can just draw the para product. All right. Let's look at one more example here. Okay, here I start with an OCH3. I start with anisole. Okay, and there's just a little typo here. That OCH3 should be drawn there, so let's draw that in. So in step 1, we're going to be adding Br2 and FeCl3. So we know that OCH3, that O has a lone pair, right? That OCH3, our methoxy group, is an ortho para director. So the bromine is added to the para position. So we started with our methoxy. We've now added our bromine to the para position, okay, in step 1. So here's the product we get after step 1. Okay, step 2, we're now going to do a nitration reaction. HNO3, H2SO4 will substitute a hydrogen for a nitro group, okay? So now we have 2 groups on here, right? We have 2 groups on here. So we have the OCH3 group. We know that that is an ortho para director. Para is blocked. There's not a hydrogen there, right? So we know that this OCH3 is going to direct our next group to the ortho position, either the position on the right or the left. This is ortho to our methoxy, our OCH3. But we also have another group on here, right? We have our bromine. Okay, we have our bromine. A bromine is also an ortho para director. So the bromine is going to direct the next group to go ortho to itself. And here we have this sort of in our gold writing. So the bromine is directing to these positions with these arrows because these are ortho to the Br. So now we have a conflict, right? OCH3 wants it to go here or here, but the bromine wants it to go here or here. So who wins, right? There's a disagreement here. When there's a disagreement, right, we have to now consider whether the groups are activating or deactivating. So if we go back to our column here, let's get a different color and let's label our groups, right? We had our OCH3, that's moderately activating, and then we have our halogen, which is deactivating. So when there's a disagreement, you're going to decide where it goes by whether it's activating or deactivating. So strongly activating is the best, then moderately, then weak. Deactivating is the worst, right? So if we scroll back here, we see that this OCH3 is activating, the bromine is deactivating, so we're going to follow where the OCH3 is directing the nitro to add. So what does that mean? We're going to be adding the NO2 ortho to the OCH3. Okay, so the NO2 will be ortho to the OCH3, and this will be the final product that's formed. And again, you could draw the NO2 on the right side or the left side. It's the same compound if you just flip it. Okay, so these are just a few examples highlighting when we're doing our EAS reactions when we already have groups on here. And what's sort of important for us is to really, really know this table, right? We have to know this table.